Now the camera is on, so don't say anything that you regret afterwards. Do you see one line across the screen now?
Yes. Yeah.
Excellent. Should we make a table maybe to collect the different values, or to have something to discuss? Do you see all these?
Yes.
So what were we did alkalinity, and we did calcium, magnesium, I think. And only calcium. What was it more?
Is it just to remind myself? Is it calcium, magnesium that is the hardness?
Yes. Yes.
All right.
And
DOC as well.
DOC. Some sulfate. Did we do chloride? That we did, I think.
Yeah.
Now let's see. 1, 2, 3, 4, 5, 6. And oxygen, wasn't that also a parameter? Anything more?
I think that's all.
Yeah. So Lake 1 was Värtan, which is our approximate sea. It's not the sea, but it's connected to the archipelago, which is in its turn connected to the Lake Baltic, and that in its turn is connected to the sea, or it is the sea. So this is more close to sea than at least a freshwater lake is. This was the strange small pot. And this is a lake called Laduviken, typical lake with some agriculture surroundings and some fields. Should be quite reasonable. Alkalinity at least. And what was this? This was Brunnsviken, yeah. Slightly less salt part, a little lake that is connected actually to Värtan, to Lake 1. So Lake 1 and Lake 4 should have similarities, while Lake 2 and Lake 3 should have some similarities. Did you calculate values for the alkalinity?
So here I wanted to ask, do you mean like the pH at the equivalency point? Because we calculated, I mean, we did a curve obviously for that, and we got the concentration of the HCO3 minus.
Yeah, I thought of the concentration actually.
Yeah, so me and Chris, we did Lake 2 and Lake, no, Lake 4 and Lake 1.
4 and 1. And what values did you got?
So on the first one, we got the concentration to be 0.0014 molar.
0.0014.
Yeah.
Yeah.
And on the fourth one, we got it to be 0.0017 molar.
Okay. Anyone more for Lake 2 and 3?
We could offer 3.12 milliequivalents per liter for Lake 2.
For Lake 2?
Surprisingly high.
Yeah. You said
312.
312.
Yes, exactly.
0. sorry, what is this?
So it could either be 0.00312 mole
Ah,
per cubic decimeter or 3.12 milliequivalents.
that's true. That's true. 3, 1, 2. So
Yes, exactly, in mole.
you mentioned this mill equivalents, and that is an interesting unit. Equivalents for 1- and 1+ ions, they are equal to the moles per cubic decimeter measure, but for 2+ and 2- ions, it's a factor of 2 involved also, because you essentially, by the equivalent concept, mean that well, equivalent to single valued ions. So, lake free, is someone? Anyone has a value for lake free?
I mean, I didn't do this one, but I have a photo of what was written on the
Yeah.
board,
Excellent.
and that was 0.029 molar.
Was it 2 zeros?
2 zeros and then 29.
Yeah. And both of these are, I mean, 0.003 and 0.00. Well, we could round them to 0.003 both, and they are, it's large values. While the 0.0,
Sorry.
yeah.
On my photograph, it's not the same number.
Yeah.
I don't know if
What do you have then?
for Lake 1, it's 0.0012.
12 instead of 14.
Yes. And yeah, it's
No, that's because we wrote, we didn't get the curve. So we just took a point like from where we thought the equivalency point would be, but when we have the graph, it's easier to see.
okay.
So yeah.
Yeah, but they are more or less equal in size, at least. Let's see some calcium magnesium now.
Yeah, but actually, the same as with Molly, you know, on the whiteboard, what was written for Lake 4 was 0.0152, so like 1 order of magnitude larger. So I'm not sure.
Something like that.
Yeah, that's what that's what my photo says.
That's wrong. I think it was my bad. I just wrote something completely else. It's supposed to be something like 0.0015 and 17.
17 or 15. That's
around
okay.
there.
Thank you for clearing it up.
But if we lack 0 here, it's 0.015. That's enormous. Then then it's something like the Dead Sea or something like that.
I have a question here though, because I got a bit confused. The volume, we used milliliters, right? For both the water that we added, or yeah, the sample water and the hydrochloric acid.
Yeah.
But so you need to do unit conversion, right?
Yes.
And I mean, I didn't do that. Got that value, the 0.0014.
Mm.
So it should be even lower, because milliliters, I mean, there's 10 to the power of -3 milliliters in DM3.
Yeah, but I don't think so. This is by accident a correct calculation, then I would say. If you have milliliter in the amount of sample water and milliliter in the amount of hydrochloric acid, those two should cancel each other. But what concentration did you have of the hydrochloric acid?
I mean, it said molar.
Yeah.
Yeah, so
moles per cubic decimeter. If this is the condition, So then you had the volume times the concentration and the volume times the concentration. If this is in milliliter and this is in milliliter, then they cancel. And the unit of the hydrogen carbonate will be the same as the unit of the concentration of the acid.
Oh, okay. Yeah, makes sense.
Yep. So calcium, magnesium.
Yeah, I have one value for Lake 1.
Yep.
It's 0.0062 molar.
Mhm. Okay, any more values?
I got Lake 3, 0.0025.
Yeah. And moles per cubic decimeter?
Yeah.
Mhm.
I got the Lake 4. It is 0.005.
Okay. And moles per cubic decimeter? Is that so?
Yes.
Anyone with Lake 2?
Yes, we did Lake 2, and
Yeah.
it's 0.00161.
Okay. So here we can see something that for Lake 1, it seems to be higher metal ion concentration than alkalinity. Even though, and also these are 2-valued ions, and the alkalinity is essentially 1 minus valued hydrogen carbonate. So it's more metal ions than carbonates. Here it's approximately half, and this is perhaps reasonable if all the hydrogen carbonate come from vitrification of calcium or magnesium minerals. Here it's actually 25, since it is 2+ ions, then it's more worth than 0.0029 or 1 minus ions. So here are more metal ions, but not as much more as in Lake 1. And in Lake 4, you have a similar situation as in Lake 1. Yes, that's okay. We continue.
I have a question. Is it usually that the seawater is harder than the lake water?
Yes, it seems so.
And is there a special reason for what is the cause of that? Is it just
possibly? I mean, normal freshwater lakes they drain out in the sea, and the sea collects all water and all corrosion products.
Okay, so it's basically all the
ions that has been collected.
Yeah, everything that has been broken down.
Yeah, end up in the sea.
The water. Okay. Right.
And calcium ions only then?
I have one for Lake 1.
Yeah.
It's 0.0016.
16, yeah.
Moles.
And any more lakes?
We had Lake 4, which was 0.00217 molar.
Yeah. And 2 and 3?
Free is 0.022. No, wait.
2 zeros.
Yes.
And do you have?
I'm sorry, but I think I had Lake 3, and I wrote 0.0019.
Okay.
I don't know how.
Yeah, we did an extra one, and there was already
Yeah.
a value there. So
Excellent, excellent. Because 22 is approximately equal to 19. Here you see a measure of how difficult it is to make an accurate analysis. I mean, the transition is not very clear. Where is this red to blue transition occurring? But these two are quite okay. No problem. Lake 2 then?
We had 0.0014.
Okay, excellent. So then, do we see some pattern here? The calcs in Lake 1 and Lake 4, it seems to be dominated by magnesium. There seems to be a lot more magnesium, or a little bit more. Here it's a lot more magnesium since the calcium is not very large. While in the Lake 2 and 3, the calcium and magnesium and calcium only is approximately equal, even here. So these seems to be dominated by calcium ions. My question then is, why is the sea or the sea lookalike lakes, why are they deficient in calcium and the majority of the 2+ ions seems to be magnesium, while the normal lakes, the freshwater lakes, are dominated by calcium ions? I mean, you don't have to answer, but you can think about it. We can continue to fill in this table. Any values for the dock or anything else here?
Yeah, we had a value for the DOC. We got it to 0.7 times 10 to the power of -5 moles.
0.7 times 10 to the -5 moles per liter or something like that. In Lake 1?
No, maybe I calculated wrong then. I wrote the substance mängd.
Oh, yeah.
Should I do the concentration for it?
Yeah, but in how much sample water?
In
It was in 20 milliliters, so I think it's around 55 milligrams per liter.
Oh yeah, yeah. That's an easier. Then we can compare maybe. Anyone else that did this analysis on the other lakes?
Yes, I got Lake 3.
Yeah.
2.28 milligrams per liter.
Okay.
We did Lake 2.
Yeah.
We did 2 samples at the same time. So we got one that was 71.1153.
Yeah, we round off to
rounded off to
271. I said yes.
Or 71.
Yeah.
Milligrams per DM3. Or per liter. And then the second one was, if we rounded off, it was 68.
Yeah. Those two are very, very well fitting to each other. So
yeah, they were, but we also had we did a blank, and we got quite a lot in the blank as well. I don't quite remember. I think it was.
I think it was 17.
Yeah. So we got
or something.
17 in the blank, so maybe not so perfect.
Was it a blank with deionized water?
Yes.
Yeah. Okay. Yeah.
So it was kind of strange because we were very satisfied with the numbers being so close together, and then we had a blank that was not so good.
Yeah. Yeah, but I mean, the blank indicates that there is a self-decomposition of the permanganate ion or some systematic error at least, but I think it is self-decomposition of the permanganate. But still, even if you remove the blank, it's quite a lot.
Yeah, yeah.
Anyone with the Lake 4?
On the whiteboard, it said 4.27. I have no idea.
No. Okay. We can take the sulfate and chloride ions instead. Anyone that did Lake 1?
Yeah, I did Lake 1 and 2, but I didn't know how to calculate this. So,
but what value did you get? Did you identify the magnesium, barium sulfate?
Identify.
Yeah, which of the barium sulfate solutions was it? Could you identify it on my pictures?
Yeah, because then that's when I got confused, like what I should do with them. So maybe I can calculate at the same time as the other lakes will show their results.
Yeah, but you can tell us the amount of barium sulfate.
So which page?
Anyone else with the sulfate ions? Either weight of barium sulfate or concentration?
So we had 27 milligrams per liter of sulfate for Lake 2.
Yeah.
I think for Lake 3.
Oh, sorry.
So Lake 2 is wrong. It's on 3.
Yeah. Anyone else? I think this was small because my picture in memory says that this is very, very tiny amounts of sulfate in Lake 2. Why? I don't know, but it seems to be a lot of organic material. And perhaps one could construct some model that should affect the sulfate levels. But on the other hand, it didn't smell like H2S or something like that. But there are a lot of other reduced sulfur compounds that could be present in the sediments, for example. I'm not sure, but perhaps. It's definitely the most the lake with the most growth in it. It's the most eutrophicated lake, or dystrophic maybe. It's not totally eutrophic. Do we have some other values? Do we have oxygen, for example?
We calculated on Lake 4, but we have in molar instead of milligram per liter.
Yeah, but we can take
I
that.
don't know.
It's better to have it.
Yeah, 2.2 millimolar.
Millimoles, yes.
Lars, is this the one we were supposed to heat up in the first lab, and then we let it cool down and?
Sorry, I don't understand. What is your question?
For the SO2-4.
Yeah.
I think we did the experiment, but I think Johan told us that he was going to take care of the rest.
Yeah.
If this is the one we heated up and then left.
Yeah.
Yeah, so we don't have any measurements or.
Oh yes, you have. I weighed all the samples and put out photographs on Athena.
Oh, sorry, I missed that.
Yep.
Then I understand. Thank you.
We can take chloride ions. Do you have that?
Yes, we have it. Just 1 second. It's 43.19 millimolar
In Lake
for
1?
Lake 1.
43, I round off. Was it millimolars? Yes. And anyone in the other lakes?
We got 5 millimolar for Lake 3.
Okay.
For Lake 2, we got 0.0025 molar.
0.025. So we continue then with millimolar. So yeah. And then one with Lake 4.
On the whiteboard, it said 73 millimolar.
Okay.
Or 74, I mean.
Yeah. Okay, then we can see a clear pattern here. In Lake 1 and Lake 4, it's high chloride ion concentration because this is said to be connected to the salt sea, while Lake 2 and 3 are freshwater lakes and do contain a quite small amount of. This is definitely a concentration that you can use as drinking water then, while I would perhaps hesitate to drink the water in Brunnsviken and Värtan. Not to taste it, but I mean to use it as a general drinking water for consumption. And also the OC is high in Värtan, quite low here. It seems to know if it's correctly calculated. I don't know. There is a factor of 10 or more differing between these two and these two. Is it a reason why?
I think that I know why it became so low. It wasn't like my lab would do the first lake, but when Johan helped us, he forgot about the part with how much volume in the sample. So he just he said that was the milligram per liter, but I think that's supposed to be well,
in the sample,
calculate it in the volume, but I don't know which volume they had. We had like 20 because it said that in the lab. So yeah, divide that by 20 and
yeah.
And we did something wrong with the Lake 3. So we got the wrong value, but Johan helped us change it. I don't know what happened, but it may be wrong.
Yeah. Okay. Yeah, it's not so serious. It's not at all serious. I mean, let's see if you got some oxygen then.
Yeah, we have values for Lake Water 4, and it's 0.25 millimolars.
Yeah. And anyone else?
We have 0.21 millimole for Lake 2.
We have 0.2 millimolar for Lake 3.
Anyone with Lake 1? Three out of 4 is not bad. But what can we say about the oxygen content of the lakes? Seems to be oxygenated water, definitely.
Yeah, the whiteboard had 0.0285 molar written on it. So that would be
0.285. Was it like that?
It was 0.0285 molar. So that would be 2.85 millimolar.
Yeah. A factor of 10 difference in Lake 1 compared to the other 3. I mean, the majority claims 0.2 and one outlier here, or this one is correct and 3 of the others are incorrect. Could, I mean, it's something like 2 to 3, and that fits the other ones. But I think this is in one of either Lake 1 or the rest of the lakes are wrong by a factor of 10 or something like that only. I mean, it's not extremely important, of course. Yeah, of course it is, but for if this is an acceptable value for fishes and vegetation, and then this is not acceptable. But this we can check afterwards. That should be no problem.
Would it not be wrong calculated?
I think it is some error, at least in the calculations. All 4 can't be correct.
Okay.
I saved the whiteboard now as a PNG file, so I can upload this one to Athena. But yeah, can we draw any conclusions from these values? Maybe it's difficult to, yeah, the conclusions for the chloride ions, they're high. And did we measure any parameter, by the way? We measured.
Lars,
yeah.
I think for Lake 4, for the chloride ion should be 7.4 millimolar.
7.4. Mm-hmm.
Yeah, not 74.
But it's still, I mean, yeah, it's less than the Värtan value, but it's higher than the freshwater lakes. Do you remember the conductivity values that we measured? I think my memory says that this was 5 millisiemens and this was 4 millisiemens or so, while this was 0.5 millisiemens and this is 0.5 millisiemens. Take it or leave it, say 10-20% errors, but obviously the salt Värtan water is definitely more conductive than the 2 freshwater lakes. I think several of you noted that when we took the conductivity at Lake 2 already, and even at Lake 3. There is an image. I did put out the values on Athena, on the main part of Athena, not below. As an anslag, I don't know anslag. What is it in English? Help me, someone. Announcement on Athena.
Lars, I checked the values that I antecknade during the experiment, and I think you avrundade the values, right? Because
Where?
I have a small difference.
Where? Where?
Conductivity. You did avrunda, right?
Yes, of course. And this is only from my memory, but give me the values.
It's not a big difference, but it's 4.90 for the first lake. 0.61 for the second one. 0.89 for the third one. And 4.44 for the last one.
Correct. Yeah, but these are quite similar to my just random memory values. They're low in the freshwater and quite much higher in the Värtan and Brunnsviken water. 10 times higher, not exactly 10, but an order of magnitude approximately. If you take the 10 logarithm of the fraction here, you will be quite close to unit or -1, depending how you do the division here. Can we draw any conclusions?
Well, I mean, we've already said most of them, haven't we?
Yeah, I think so. Calcium, magnesium is a tricky thing.
You just take the difference between the two values and then you determine which one is more present. Yeah.
Then you can, in principle, calculate an extra row here. Say that we would do the magnesium 2+. So here it would be quite 62 minus 16. What is that? 46, is it? And then you see that it's a lot more magnesium. 16 minus 14, then that's not so much. Very small amount of magnesium. 25 and 22, then you would have something like 0.0003 there also. Very low amount compared to the calcium amount. Here it's, if you take this as 22, then it would be something like 28. This is approximately equal or a slight surplus of magnesium ions. Interesting, because this is approximately the pattern that distinguishes seawater from lake water. And here you have a possible way of determining whether your unknown water in a crime series or something like that come from the seaside or from a lakeside.
I have a question.
Yes.
Did somebody measure the concentration of sulfate in Lake 1? Because I see that it's missing in the table. Yeah. I don't know if you took notice.
I don't know if someone did. Someone did, I think, but maybe.
And also, I think we had like 3 groups that did Lake 1, so it wasn't just me. I don't know which. We did like a lot of samples of one lake.
Yeah.
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 I'm trying to calculate it now.
But I mean, if it's then in order to compare the sulfate ions, you need to have the same unit. So milligrams per liter is quite okay, but then you need millimoles. The sulfate ion is 16 plus 64. No, 32. Sulfur is atomic weight is 32, and 4 oxygens is 64. So 94, 96 is approximately 100. So this will translate approximately to the same in milligrams per liter, to the same figure, 2.2. No, times 100, yes, 2.2 millimoles times 100 is 10 times bigger than that one. something like 200 milligrams per liter. Is it really that much higher? Could be. But millimoles, 2.7 millimoles is perhaps a high value. I don't know where are there any sources of sulfate in Brunnsviken? Could it be from the yacht club? In the inner part of Brunnsviken, there are some small boats, not only sailing boats, but also normal traditional motorboats that would pour out sulfur, SO2 maybe content from gasoline and such things. That would maybe not. I don't know, but it's not unrealistic. It's something like a reasonable level. Maybe the sulfate ion concentration in Ladoviken is perhaps small, or it could be erroneously calculated. This is small, that I definitely know, because it was very, very small amount of sample barium sulfate that was precipitated.
Can I ask, like, how do you, because for the DOC, I've written it in moles. How do you go to milligrams per liter?
Yeah, you multiply by, say, if it's oxygen, then by 32, then as the molar weight of oxygen.
Oh, okay.
Or I mean, this DOC could also be this permanganate number. Then you multiply by the
permanganate.
Potassium permanganate, which is 150, slightly more.
Then it's weird, because then me and Chris have gotten different values, I think. But we did the same experiment. I don't know. We'll talk about.
Do you have a 1.1 or?
Yeah,
because that's the thing I talked about earlier. I think Johan gave us the wrong like last value, because he didn't include that it was in the volume of the sample. So he only gave us like the gram, so not the gram per volume, which was what the lab asked for. So I just took 1.1, then let's see. I'm just gonna
multiply by 50 then, or
sorry, I'm trying to find it.
It should be.
It's the no, I think I'm true. It's just 1.1 divided by 20.
And divided by the volume.
So it's the mass divided by the volume, because the 1.1 is just the mass of permanganate in milligrams. So we take milligram per 20 milliliters. And then you get 55 milligram per liter.
But isn't it the moles? Isn't it the moles of permanganate that we thought?
but the lab asked for in the end to have it in milligram per liter. That was why I did it.
So then by multiplying it with the 158, you get the grams, and then you divide it by 20. That's what you mean. Okay, I think.
No, if you have 1.1, you just have to divide it by 20.
Okay.
Yeah, because what we had at the end of the lab was the mass.
Oh, right. Oh, sorry. Yeah, okay. I confused myself.
I just like realized when I got home that we never divided by the volume, but I think he forgot about that as well, because he wrote milligram per liter when he said 1.1, but we never divided by liter. So that was all. But it's the same. We have the same. It's just the last part.
Okay, great, super, thank you.
I'm a little interested in the alkalinity, as it's, you know, it's higher, almost pretty much exactly. It's about twice as high in the lakes that were surrounded by a little bit more, in the smaller lakes that were surrounded by a little bit more farmland. Was there something, I'm not sure, but I felt like you said something during the day when we collected the samples that there could be an effect, that the farmland itself could have an effect on the alkalinity.
Yeah, definitely, because when rainwater filters through the ground in the farmland, it could drain out and dissolve some minerals, or the rainwater contains dissolved carbon dioxide, and when that slightly acidic solution, when it filters through the farmland, then it can vitrify some minerals, and well, what will end up in a lake is essentially not as acid rainwater, but probably the vitrification products from the filtration in the farmland.
Okay, so they dissolve some minerals.
Yeah.
That are in. Okay, and it's specifically, so does the minerals themselves, what are the minerals that are specific to the farmlands?
Yeah, it's I mean, the simplest are calcium or magnesium carbonate, but they do occur at some places, but not generally in large amounts. So otherwise it's silicates and a lot of different minerals, but all of them is do have a slightly basic character. So they will dissolve carbonic acid or react with the carbonic acid, and at least the carbon from the carbonic acid will be transformed to hydrogen carbonate, which will end up in the lake.
Yeah, I see how the calcium carbonate could be dissolved into, you know, carbonate ions that could turn into hydrogen carbonate. But why are the calcium carbonate and the magnesium carbonate, why are they found more in farmland than just in the forest or any other place that the rainwater drains towards the lake?
Do you mean the farmland, lakes, and the sea, or?
Yeah, and the sea as well as Brunnsviken.
Yeah, exactly. It seems to be something that consumes calcium ions in the seawater. And a simple explanation is shellfish. That is different type of plankton, or even larger shell constructing animals that live in the water, like musslor in Swedish, and snails and such things. Okay. And they consume more calcium than magnesium. Some of them can also use magnesium carbonate is more soluble than calcium carbonate. So if you should if you're an animal living in water and you should grow a shell around you, you would prefer calcium, actually, because calcium carbonate would do a stronger shell.
Okay, so in regards to the alkalinity in the lakes, so then you'd say that the alkalinity is not higher in the you know, smaller lakes because there's a larger inflow, but rather because there are less organisms consuming the,
probably, yes, less organisms,
calcium, which in turn would turn
freshwater lakes, that is painful for living organism, I think. Then you have a lot of osmosis that kills most. If you compare the size of the organisms that live in freshwater lakes and the size of corresponding organisms that live in seawater, so the seawater organisms, they are 10 times bigger or something like that, or a lot bigger.
Okay.
Not I mean, it's you living in a freshwater lake. You need to use a lot of power or energy in order to actively see to that you're not osmotically destroyed, so to say.
Okay, so that would be why you think the alkalinity is higher in the small lakes. All right, That,
yes, yeah.
That was one of the large difference I feel like when you look at this diagram, along with the, of course you have with the DOC, but then you had a little bit.
Yeah, that is the DOC is difficult, but the alkalinity is higher because it's less, and it's also, I mean, in Lake 2, it's approximately twice as high alkalinity as calcium magnesium. This is exactly a product of dissolution of calcium carbonate with carbonic acid from the atmosphere. Then we would have some kind of then we would have some kind of fraction like this. 30, if we round this to 32 and 16. While in the seawater, we have a lot more ions than alkalinity. And there is something else also coming from above, not necessarily from carbonic acid, but there are hydrogen ions from, for example, sulfates or sulfur dioxide or sulfur trioxide from burning of fossil fuel. Maybe nitrogen oxides. They produce some acid substances that give rise to H+, and that will consume alkalinity in the sea. At least in a harbor environment like Värtan is. Heavily affected by hydrogen ions, acid depositions, while the metal ions, they don't care about the acidity. It's no problem. They can coexist. But here in the freshwater lakes, it's hardly any, not so much. They are not so much dependent on the gases from the atmosphere. Well, from burning of fossil fuels, for example, they always contains sulfur, which is dissolved and more closer to the actual source of the production of the sulfur oxides. Could be a reasonable hypothesis, at least.
I wonder something.
Yes.
But firstly, we had a value for Lake 1 sulfate, which was 2.64. Thanks to Felice.
And what unit? Millimoles?
But the question was this. Is it possible that sulfate could come from like the water runoff from roads?
Yeah, but I mean, this sulfate ion concentration, you find it in the Atlantic also, approximately in the order of millimoles. So water runoff from roads.
Yes, but I was thinking about the larger values.
Yeah, I mean, it's if you have some very high value, I don't. If it will be 10 times higher, then you should have a local source of sulfur. Yes, but otherwise, I think sulfur oxides, they are emitted from volcanoes, for example. Which has been erupting and spitting out sulfur oxides for millions of billions of years. So there are probably sources for all of that sulfur. It's a tremendous amount of sulfur in the oceans. But then humans also add up to them to the concentration by burning fossil fuels.
So could, like, when the car burns its fuel and the exhaust comes out, then it will have some sulfate.
Yeah, it will.
And could that then, for example, if it was raining outside, could the sulfate in the exhaust get dissolved into the water on the ground?
Definitely. That is a source, but I mean, it's not the only source. There has been historic filling up of sulfates over a long time, but especially nowadays in some areas of the world where there live a lot of people burning a lot, then burning a lot of fossil fuels or wood, then you end up with higher amounts of sulfur oxides in the atmosphere, and when the rain then leaches out the sulfur oxides, then the ground gets more acid. So say Europe, Middle Europe is more acid ground than, say, somewhere in northern Sweden where hardly anyone lives or no industries. Hörni, by the way, could we make a break, because I would need to speak to some other students now in another course also. Or I'm not sure, can we join in an hour or so?
Can I just ask quickly if did we come to a conclusion with the calcium and the chloride, like the correlation between them?
No, there is a correlation, yes, but the calcium, magnesium, and the chloride, that is no correlation. This is typically sodium chloride. That gives the high conductivity as well as the high chloride ion concentration.
I was wondering if we're gonna take a break, like how much more is there to discuss? Because I feel like we discussed
not much.
Are we gonna take a break for an hour and then like have 10 minutes?
Yeah, in the worst case. Let's say that you send me mail if you want to have yet another seminar. We have a seminar also on Monday.
I had questions about the lab report, but maybe I can email them to you.
Yeah.
I don't know.
Yeah. Okay, but then we you can connect at 3 o'clock approximately here. So.
Yeah. Okay.
Okay. Thanks.
Can I ask something really quick?
Yes.
Because I managed to get confused about the calibration curve for lab 2.
Yeah.
The concentrations for the standard mixtures, was that from 10 microgram per liter up to 160? Okay, yes. Okay, thank you.
And for that lab, do we have to add anything to it, or what?
No.
Okay, should we just showcase the standard curve in the same lab report maybe as the first one?
Or you can skip it.
Okay. Okay. All right. Yeah.
And the conclusion is hardly any phosphate.
Yeah.
Yeah. One line lab report.
Yeah.
Okay.
Great. Okay.
Eventually see you at 3 o'clock then.
See you. Bye-bye.